Hello and welcome to today's revision session on magnetic fields, which is part of the AQA A-Level Physics specification. So in today's lesson we're going to look at reviewing the concepts of magnetic fields. Now the first topic we're going to look at is magnetic flux density. Now in previous topics like electrical fields and gravitational fields we've already covered the concept of fields. Now a field is a region of space where a non-contact force can be exerted. Now we're going to build on this prior knowledge to understand what magnetic fields are. Now with an electrical field we know that charged objects produce an electrical field, and if another charged object is placed inside the electrical field it will experience a non-contact electrostatic force. Now charged objects also produce a magnetic field as well as an electrical field. So if another charged object is placed inside a magnetic field it will experience a magnetic force. Now the magnetic field and the electrical field of a charged particle will always be at right angles to each other. Now there are two types of charged objects we must consider that experience a magnetic force when they're placed inside another magnetic field. We've got macroscopic objects and we've got microscopic objects. Objects on the everyday scale and objects on the particle scale. So an example of a macroscopic object could be a current carrying wire, and an example of a microscopic object could be a charged particle. Now we've got both objects experience a magnetic force when placed inside another magnetic field. Now we've covered this idea of the magnetic force exerted on charged macroscopic objects at GCSE, but this idea of the magnetic force on charged microscopic objects was linked into particle physics, which you looked at earlier in the AQA A-Level Physics specification. Now the equation to work out the magnetic force on a macroscopic object like a current carrying wire is magnetic force is equal to magnetic flux density times by current times by the length of wire, F equals BIL. Now the equation for the magnetic force on a charged particle is magnetic force is equal to magnetic flux density times by the charge of the particle times by the velocity of the particle, or F equals BQV. Now we can amend this to consider electrons by looking at the charge of an electron, 1.6 times 10 to the minus 19 coulombs, by calling this F equals BeV. So we're going to now look at these concepts over the next couple of slides in this particular lesson. So let's consider the magnetic force exerted on a current carrying wire when placed inside another magnetic field. Now in this situation the magnetic force occurs due to the interaction of the charge of the wire and the magnetic field of the permanent magnet. So the charge of the wire only occurs as the wire becomes an electromagnet when a current passes through it. So the charge of a wire only works when we consider this idea of the principles of electromagnetism. So the idea is when you have a wire with an electrical current passing through it, the wire also produces a magnetic field. Every electrical wire will also become a magnet. Now this occurs because in this particular object you have domains in the form of free electrons. So a moving charged particle will produce an electrical field and a magnetic field at all time, which is why it's impossible to get an electrical current without a magnetic field. So there is always an electrical field and a magnetic field which exist at right angles to each other. So this means that the magnetic field lines around a long thin wire are circular, so around a wire you get a magnetic field which is formed as concentric circles around that wire. Now the fact that magnetic fields and electrical current are at right angles can mean it can be quite difficult to draw on a 2D shape such as a piece of paper, but you've always got to show it. So let's now just consider the basic principles of electromagnetism before we look at some applications of this. So there are four basic principles. When an electrical current flows in a wire, a magnetic field is formed around a wire. The stronger the current, the stronger the magnetic field will be. When a current stops flowing in a wire, there is no magnetic field, and if the current changes direction in a wire, the magnetic field changes polarization. So we can use these four basic principles to work out different effects that a current carrying wire will undergo. Now we can draw these electromagnetic fields, the electrical field and the magnetic field, by considering a couple of rules. Now like we said before, the electrical field and the magnetic field are at right angles to each other, so the magnetic field will form as circles around the wire perpendicular to the current flow of the charge in the conductor. Now there's a law which can help you remember how to draw the magnetic field around a current carrying wire correctly. So if we consider a current carrying wire, the magnetic field will form as concentric concentric circles around that particular wire. Now we can call this idea the magnetic flux, and the higher the magnetic flux density, the stronger the magnetic field. Now in this instance you would get a higher magnetic flux density if the current through the wire was increased. Now the rule to determine the direction of the magnetic field lines from a current carrying wire is called the right hand rule. So as electrical current passes through a straight wire, your thumb of your right hand points in the direction of current. Now to clarify, this is conventional current flow, not electron flow, and the fingers point in the direction of the magnetic field from north to south. So the current, as we said before, moves in the direction of conventional current, so from positive to negative, which is in the opposite direction to electron flow. Now if you consider this rule, this means that if you reverse the direction of current in a wire, you'll reverse the magnetic field direction produced by the wire. So it will change the north and south poles of an electromagnet, which will be important when we consider alternating current later in the course. Now it's also important to note that this is a simplified magnetic field if the electrical current runs through a single straight wire. Changing the shape of the wire can change the shape of the magnetic field produced, but you can observe this effect of the magnetic field by using iron filings. So you'll notice that when we place iron filings around a current carrying wire, they form field lines of concentric circles. Now just be careful to not confuse the left hand rule and the right hand rule when you are carrying this out. Now as we mentioned before, as the electrical and magnetic field causes charged objects to accelerate, there must be a force in this situation. So a gravitational field provides a gravitational force, whilst an electromagnetic field provides an electromagnetic force. So the magnetic force is produced by the two magnets interacting with each other and produces a force perpendicular to the current and the original magnetic field. So we tend to give the name of the magnetic force as the Lorentz force, but we're just going to refer to the magnetic force in this example. So let's have a look at a few examples of electromagnetism. So let's consider a long thin wire, which we can also call a solenoid. When a current passes through the wire, it produces a magnetic field. Now all current carrying wires produce a magnetic field, and the direction of the field lines is given by the right hand rule. The stronger the current flowing through the electromagnet, the stronger the magnetic field. No current flowing through the wire, no magnetic field is produced. Change the direction of the current flowing through the wire, the polarization of the magnetic field changes direction. Now you can consider the principles of electromagnetism by also looking at permanent magnets, which are materials that always have the domains line up and have a constant magnetic flux density. So the magnetic field from around the wire and the magnetic field from the permanent magnet will add together, which causes a resultant field to be found, and this then allows a force to be exerted on both of the objects. So the magnetic field from around the current carrying wire and the magnetic field from the permanent magnet add together, and we can produce a resultant field in this situation. Now you'll notice that below the actual wire, the field lines from both the permanent magnet and the current carrying wire are in the same direction, so the field lines will add. So below the wire you've got a high magnetic flux density. You'll notice that above the wire, the magnetic field lines from the permanent magnet and the magnetic field lines from the wire are in opposite directions, so they subtract each other, and therefore you get a low magnetic flux density above the wire. So below the wire, a high magnetic flux density, a low magnetic flux density above the wire. The difference in magnetic flux density produces a resultant force in the direction of the low magnetic flux density, which causes our wire to be pushed. So the bunched lines produce a pushing force on the wire. Now also just be aware that this is a third law pair, so whilst there is a resultant force acting on the current carrying wire, there is also a resulting force acting on the permanent magnet. But because the permanent magnet is much larger, it does not accelerate as much due to the equation F equals ma. So just to clarify, this force is called the magnetic force, and is produced by the interaction of two magnets on each other. It's the magnetic equivalent of Coulomb's law or Newton's law. Now like we said before, both objects, the wire and the magnet, experience the magnetic force, and the size of the force depends on the component of the magnetic field that is perpendicular to the current. So what we remember is that the magnetic force is perpendicular to the current and the magnetic field, so therefore What we can then do is consider this idea in terms of the direction of each. So remember, the electrical field, the magnetic force and the magnetic field are all at right angles to each other, and there is a trick to learn in the direction of movement in this particular idea. There's a trick to learn in the direction of the magnetic force, and it's called Fleming's left-hand rule. So this allows you to work out the direction of the magnetic force and therefore the movement on the wire in any situation. So with your left hand you will have your thumb up as shown, and that will show you the direction of this magnetic force. Your first finger should be pointed outwards. The north pole is at your knuckle, the south pole is at your nail, and therefore the first finger shows the direction of the magnetic field. The second finger will be moved like you'll be swearing. The second finger shows the direction of current, with the plus at the knuckle and the negative at the nail. Now you must always change the position of your hand to align your fingers with the correct direction of the known quantities in the problem. So you will always have your thumb in the direction of the magnetic force, your first finger in the direction of the magnetic field from north to south, and your second finger in the direction of current flow from plus to minus. Now we did actually cover this concept in GCSE physics. So in any question, you place your knuckle of your first finger at the north pole of the permanent magnet and point your finger to the south pole of the permanent magnet. In the second step, you'll place your second finger pointing in the direction of conventional current flow. You may have to reorientate your finger to ensure step 1 and step 2 are satisfied simultaneously, and therefore the direction your thumb points in is the direction of the magnetic force and therefore the direction of movement on any wire. So when a current carrying conductor is placed in a magnetic field, the magnetic force producing the field and the conductor exert a force on each other. So the magnetic force is caused by the conductor cutting across the flux. So this is because the magnetic field of the conductor and the permanent magnetic field are interacting, and you can work out the direction of the force by using Fleming's left-hand rule, which in this situation is indicating that the magnetic force acts out of the board. Now you've got to be aware the maximum force is caused by when the magnetic field of the permanent magnet and the electrical current of the wire are at right angles to each other. There is no force produced when the magnetic field of the permanent magnet and the electrical current are parallel to each other. This is because no flux is being cut by the conductor at this point. The conductor is straddling the flux. So what factors affect the magnetic force produced by the interaction of the magnetic and the electrical fields? Well, you've got the magnetic flux density. The greater the magnetic flux density of the permanent magnet, the greater the flux cut by the conductor, the greater the force produced. You've got the length of the conductor in the magnetic field. The greater the length of the conductor in the field, the greater the flux cut by the conductor, the greater the force produced. Now the last one is the current going through the wire. The greater the current through the conductor in the field, the greater the flux cut by the conductor, the greater the force produced. Now we can then link these together in an equation, and it is as follows. The magnetic force on a current carrying wire is equal to F, which is equal to BIL, the magnetic flux density in Teslas times by the current in amps times by the length of the conductor in the field in meters. Now the term magnetic flux density, how close the magnetic field lines are together, can also be called the magnetic field strength. Now this week, when we do this equation, the only length which is considered is the length of the wire inside the external magnetic field, because that's the only part of the conductor which is cutting magnetic field lines of the external magnet. Now in this instance, in the question, you would not use 25 centimeters, you would use 20 centimeters, because that is the value of the wire which is actually inside the magnetic field. Also be aware, if a loop of wire is used, then it's the total length of the wire in the external magnetic field. So in this particular example, the length you would use in the equation will be 40 centimeters, because there are two 20 centimeter lengths of wire in this magnetic field. Now when we look at this equation, F equals BIL, this equation is only true if the magnetic field and the conductor are at right angles to each other. This is when the maximum possible force is produced. So the more thorough equation for this is actually F equals BIL sine theta, where theta is the angle between the magnetic field and the conductor. So we sometimes call this equation the Bill equation, the equation to calculate the force exerted on a wire carrying out a current by another magnetic magnetic field. Now remember, an equal but opposite force is exerted on the magnet producing the magnetic field interacting with the wire. That's Newton's third law. So this Bill equation is the general equation for a large conductor found on the scale of motors. Now we can rearrange this equation to define the Tesla. So B is equal to F over IL, so 1 Tesla is equal to 1 Newton per amp per meter. So this is the definition which needs to be memorized. So learn the following definition. 1 Tesla is the magnetic flux density of a wire of length 1 meter carrying a current of 1 amp as a force of 1 Newton is exerted on it in a direction perpendicular to the flux and the current. Now it's important to note that we actually define the amp based on this particular equation, so we can rearrange it and say current is equal to magnetic force over length of wire times by magnetic flux density, which allows us to give our SI base quantity definition of the amp. However, in 2019 it was slightly redefined to make it more intuitive and easier to realise, so we can work that through. So when a current carrying wire is placed inside another magnetic field, a force is exerted on this current carrying wire. The force occurs due to the interaction between the magnetic fields of the wire and the permanent magnet, and the direction of the force can be determined by using the left hand rule, where F is equal to BIL. That's a very important idea. Now remember that due to Newton's third law, that if a permanent magnet exerts a force on the current carrying wire, then the wire exerts an equal but opposite force on that permanent magnet. So remember that while there's a force on the current carrying wire, there is also an equal yet opposite force on that permanent magnet. Now as mentioned previously, the angle that the current carrying wire makes with the magnetic field affects the magnetic force produced. Remember, there is a maximum force if the conductor is parallel to the magnetic field, whilst there's no force when the magnetic field and the current carrying wire are parallel to each other. So if the maximum force is caused when the two are at right angles, we can say the angle is equal to 90 degrees, and when there is no force, when the angle is equal to 0 degrees. So we therefore understand that the term in the equation was linked with sine, because sine 90 equals 1 and sine 0 equals 0. So therefore we know it must be the sine term. So we must introduce this term into the equation, so we can say F equals BIL sine theta, where theta is the angle between the conductor and the magnetic flux of the permanent magnet. So this works out, remember, the force exerted on the current carrying wire being in the magnetic field of an external magnet and the force placed on that external magnet. So the magnetic force can have an interesting effect if we place a current carrying conductor in a permanent magnetic field on a balance. So remember, the interaction between the current carrying conductor and the permanent magnet would lead to a magnetic force being produced. Now let's consider both a conductor and a chassis which houses a permanent magnet. Now if we ensure the magnetic force on the wire is acting downwards, what would happen to the weight of the chassis on the balance? Well, the weight of the chassis on the balance would appear to decrease slightly, because the magnetic force on the wire is acting downwards, so it means the magnetic force on the chassis is acting upwards, so therefore it is the chassis that is being measured by the balance. So because you've now got an extra force acting upwards, the resultant force acting downwards on the balance has decreased, so therefore the reading on the balance will decrease, so it will appear as if the weight of the chassis would decrease slightly. Now this means if the balance was at 0, the balance would read a negative value. Now if we indicated that the magnetic force on the wire was acting upwards, what would happen to the measured weight of the chassis? Well, the measured weight of the chassis would be going higher, because if there's a magnetic force on the wire acting upwards, there must be an equal yet opposite force on that permanent magnet acting downwards. So the weight of the chassis has increased, because it appears that the resultant force acting downwards, which is being measured by the balance, has increased. So this therefore it means the weight of the object would appear to increase slightly. So if the balance was at 0, the balance would read positive. Now this is the experimental technique used to measure the magnetic flux density of magnets, as the other values can be easily determined from other measurements, because we can say magnetic flux density equals F over IL. We can measure current through the conductor with an ammeter. We can measure the length of the conductor in the permanent field of the magnet with a ruler. So therefore we can also determine magnetic force by using the balance by doing change in mass times by the gravitational field strength, and we can use these quantities to determine the magnetic flux density, the magnetic field strength of a magnet, but it's only true if the current carrying wire and the permanent magnet are perpendicular to each other. If not, you've got to consider the sign term in the equation. So if we look at an example question, we can say that magnetic force is equal to the change in weight. So the change in weight is equal to the change in mass times by the gravitational field strength. So you can work out the change in weight in that particular idea. We can then say magnetic flux density is equal to F over IL. You can have L in the question, you've got I in the question, you pop all your values in, we get 0.31 Teslas, but then the assumption of this is that the conductor and the external magnetic field are perpendicular to each other. Right, in the next part of this revision video, we're going to look at moving charges in magnetic fields. So we've got to consider the force placed on a charged particle when it's in a magnetic field. Now when a charged particle moves, such as in a current, it produces its own magnetic field. So when placed inside another magnetic field, the two fields interact, and this produces a resultant force on the charged particle. Now you observe this force in the macroscopic world as the force on the wire, which is the cumulative effect of the forces on all the different charged particles. However, we can work out the force exerted on an individual charged particle, because if we know F equals BIL, well, we know I is equal to Q over T, and we know that L is equal to V times by T. So we pop those in and we can cancel out the T terms to get our equation of F equals BQV, which is the equation for the force exerted on one charged particle. So we can therefore consider a charged particle, such as an electron, passing in a magnetic field. So if we assume the current flow is from left to right and is caused by having an electrical field present, and the electrical field acts in one plane and the magnetic field acts 90 degrees in another perpendicular plane. So let's just consider plus and minus in the horizontal and north and south in the vertical. So it's difficult to show on a 2D screen, but I have to visualize this. Now I'm going to remove the electrical field notation because we're considering a magnetic field, but it is still present. So let's consider, okay, the magnetic field acting out of the page, which we understand from Fleming's left-hand rule. Now we know that the electrical force acts in the direction of current flow, and the magnetic force and the electrical force are perpendicular to each other. So therefore this tells us that we can work out what's going on with each situation. So remember, the path of a charged object is not parabolic in this instance because there's a resultant force in both the vertical and the horizontal plane. There's no inertia in either plane of motion. So therefore we can look at the fact that it's a circular motion, not a parabolic one. Now we can work out the magnitude of the force with the equation F equals BQV. Now remember, if it's an electron, Q can simplify to E, which is 1.6 times 10 to the minus 19 coulombs, and this force makes the charged particle deflect to the oppositely charged pole. So a negative will go to north, a positive will go to south. Now we can look at this Bev equation in a little bit more detail. It is the Bill equation but for one particle only. Now if a charged particle is not moving, then it doesn't produce a magnetic field, so it would not interact with the external magnetic field, so the magnetic force would equal 0. So it would mean it would just not move towards that north pole, which makes sense because the particle is not moving. Now the equation will only work if the magnetic field is acting at right angles to the velocity of the particle. So the magnetic field is acting as a centripetal force, which we understand from the left-hand rule. Now if they weren't at right angles to each other, the equation is amended to say F equals BQV sine theta. So from using the left-hand rule we can determine the force. So in this example the force is acting out of the board. So if we take an overview of this motion, the two forces are at right angles to each other. So this means the magnetic field accelerates the charged particle via deflection because it's perpendicular to motion, whilst the electrical field accelerates the charged particle by changing its speed because it's in the same direction as motion. So therefore this gives us our circular path. Remember, it's a circular path because we've got a resultant force in both planes, so they will combine to form a circular path of an object, not a parabolic one. But the magnetic force is acting as the centripetal force because it's acting perpendicular to motion. So because we know the centripetal force is equal to the magnetic force, and we know centripetal force therefore is equal to BQV, we can simplify this by saying mv squared over r equals BQV. We can then cancel out some of the terms here, the v's on each side, so we can rearrange this and make r the subject, and therefore say r, the radius of the circular path, is equal to mv over bq. So the radius of our deflection is equal to mv over bq, which shows there are four factors that affect the velocity of a charged particle in a magnetic field: the mass of the particle, the radius of deflection, the magnetic flux density of the magnetic field, and the charge of the particle. So in both of these examples, we can actually band together the mass and the charge of the particle together with a specific charge, and therefore we can link that together and indicate to us that is also a factor, we could simplify it, that affects the radius of the deflection. Now we can use this equation to determine how changing a factor would alter the radius of deflection. Now this equation is not given to an examination. It's a marking point to remember that the magnetic force acts as a centripetal force for a charged particle. Now if you wanted to maintain the radius of the charged particle's motion, you need to keep the speed and the magnetic flux density of the field in proportion to each other, because you can't really affect the specific charge of a particular particle. Now remember, the centripetal force is equal to the magnetic force, so therefore we say R is equal to mv over bq. Now we know mv is the momentum, so you can also say R is equal to p over bq. So what we're saying is the momentum of a particle is directly proportional to the radius of its circular motion. The greater the momentum of the particle, the larger the arc of circular motion. So the more massive a particle, or the faster a particle moves, the greater its arc of circular motion. Now an application of this is in a particle accelerator such as a cyclotron, where the particles are held to a spiral trajectory, a circular path, by a static magnetic field and an accelerating but rapidly varying electrical field. So the magnetic field deflects the particle, the electrical field accelerates the particle. So the cyclotron is used in hospitals to produce high energy beams for radiation. Now it consists of two semicircular cavities which we call Ds. There's a uniform magnetic field applied perpendicular to the Ds, and an alternating voltage and alternating electrical field is applied between the Ds. So the charged particles are directed into one of the Ds near the center of the cyclotron. The charged particles are deflected into circular motion by the magnetic field acting as the centripetal force. So therefore the magnetic field makes the charged particles follow a circular path and leave the electrode. So as the charged particles increase in speed, the radius of their deflection increases, because R equals mv over bq. So v is getting bigger, R is getting bigger, so the particles follow that increasingly spiral path. Now as the charged particles cross the gap between the Ds, the alternating voltage reverses, so they're accelerated into 1D, where they're once again pushed onto a circular path by the magnetic field. On emerging from the second D, the voltage reverses again and accelerates the particle back into that first D, where the process repeats and repeats and repeats. Now if the potential difference was not alternating, the particle would slow down after leaving that second electrode. So alternating the voltage can change in a periodic fashion, as the time for the D to move in a D does not depend on its speed, because if time into moving a semicircle is pi r over v, well therefore we can pop that into the equation pi m over bq, which occurs from subbing in R equals mv over bq. Therefore it shows that the time equation does not contain a velocity term, showing that the velocity of the particles is not affected by the time it spends in the D. This makes sense because when the velocity increases, the arc of the circular path increases to compensate and keep the time taken to be constant. Now therefore we can then work out what's going on in terms of our cyclotron. So the electrical field accelerates the particles, so the radius of the path increases from R equals mv over bq. Now we can also link this into the frequency of the alternating voltage required by saying frequency is 1 over time period, so it's 1 over 2 pi m over bq. Remember, we're doubling the time to move in a circle from a semicircle, because it's obviously double the actual value there. So what we can then do is we can therefore say frequency is equal to bq over 2 pi m. Now in most recent years, a more famous example of a particle accelerator is the Large Hadron Collider. Now the magnetic field in the Large Hadron Collider acts at right angles to the movement of the charged particle. This means they deflect the particles and not change their speed. Now the Large Hadron Collider is not a cyclotron. The radius of a particle beam remains fixed in its structure, so therefore it means R must remain constant, so therefore we say R equals mv over bq. But in a synchrotron such as the Large Hadron Collider, the radius of the particle beam must always stay fixed, unlike a cyclotron, because the radius of the particle beam has to do this, otherwise because the structure is too large to change its value. So because the radius of the beam must stay fixed, therefore we mean we've got to alter mv and bq in the same proportion to indicate that they will always have the same value of R. Now, this also means that the increased B value would cancel out any increased V value, because if this doesn't take place, then these particles will collide with the side of the wall and not the other particles. We're now going to look at magnetic flux and flux linkage. So when we looked at the idea of magnetic fields previously, we can visualize the effect of magnetic fields by drawing magnetic field lines. So for example, in bar magnets, in examples of current carrying wires, or anything which produces a magnetic field like a star, for example. Now, the magnetic field lines give us a measure of the total magnetic field. Another name for magnetic field lines is magnetic flux. So we can actually define magnetic flux as the total number of magnetic field lines passing through a defined area. In simplified examples, the area is considered to be perpendicular to the magnetic field. So we can call this the magnetic flux. So remember, we measure this in Webers or WB, and this defined region can be any area. It's the area most suitable to a situation. So the magnetic flux is a measure of the total number of field lines passing through a defined region of space. So we can say it is the number of field lines in 1 meter squared when we are considering magnetic flux density. So it's slightly different to magnetic flux. Now, this means that magnetic flux density is a measure of the number of field lines passing through a defined region of space per unit area. And we measure magnetic flux density in Teslas. So since flux density is the flux per unit area, 1 Tesla is equal to 1 Weber per square meter. So let's just clarify this. The magnetic flux is the total number of field lines in a defined region perpendicular to the magnetic field. It gives an indication of the total magnetic field of a magnet, and it's measured in Webers. Now, we give it the symbol phi. Magnetic flux density is the number of field lines in a region per unit area perpendicular to the magnetic field, and it gives an indication of the magnetic field strength of the magnet, which is measured in Teslas, and we give it the symbol B in equations. Now, we can link these two quantities together with the equation magnetic flux is equal to flux density times by area. So Webers are equal to Teslas times by meters squared. So we can link that into symbols by saying phi is equal to BA, and rearrange that to say B is equal to phi over A. Now, this makes sense as the magnetic flux density is the flux per unit area. Now, in this example, we are assuming the shape is perpendicular to the magnetic field. But what happens if it's not perpendicular? We've got to use trigonometry. So therefore, let's consider now our conductor not perpendicular to the magnetic field. So we now know the component of the field is now B cos theta, because cos theta is equal to adjacent over hypotenuse. So therefore, cos theta is equal to component over B. So component equals to B cos theta. So we pop this into the equation. So say phi is equal to B cos theta times by A, which is the full equation which links magnetic flux density and magnetic flux. Now we can link this into the real world, because in the real world our wire is not infinitesimally thin but has a thickness of n turns. So we now put them onto both sides of the equation. So now n phi is equal to B cos theta times by A times by n, which gives us the equation n theta times by B A n cos theta. Now, to symbolize the impact of adding the number of turns of wire to the equation, we call n phi the flux linkage. The flux linkage is the linking of the magnetic field of the conductor of a coil when the magnetic field passes through the loops of the coil. So the magnetic flux density is the product of the magnetic flux and the number of turns on a coil through which the field passes. It gives an indication of how many magnetic field lines pass through a conductor in a chosen region of space. Now, even though turns of wire is a dimensionless quantity, we call the units of magnetic flux linkage Weber turns to differentiate between magnetic flux and magnetic flux linkage. Now, Webers and Weber turns do have the same SI base units, but we do this to differentiate between the two quantities. Now, it's very tempting in this particular type of question to cancel out n because there's n on both sides. However, don't do this, because magnetic flux linkage is very important in electromagnetic induction, because the induced EMF in electromagnetic induction is directly proportional to the rate of change in flux linkage for a conductor. This is Faraday's law of induction. Now, we'll remember that flux linkage can be altered by changing the magnetic flux density of the magnetic field, the area of the coil of the wire, and the number of coils of wire. And in addition, the angle between the flux and the area also affects the flux linkage. Now, the greatest flux linkage will occur when the area of the coil is large as possible, the greatest number of coils of wire is used, and the magnetic flux density of the magnet is at its highest, and the flux and coil are perpendicular to each other. So what about electromagnetic induction? Now, if we place a conductor in a magnetic field, there's a magnetic force acting on the conductor. If there's a relative motion between the magnetic field and the conductor, this could be due due to the conductor moving, the permanent magnet moving, or both objects moving relative to each other. Now there's also an equally and opposite force on the permanent magnet, but in this example we're not going to consider it. Now in this example from Fleming's left-hand rule, we know the motion of the conductor that is going to be acting out of the board. Now the force on the conductor is an accumulation of individual forces of the electrons in the conductor. Now each electron in the conductor experiences a magnetic force, and we can determine the direction of the magnetic force with the left-hand rule. Now the force on the conductor will then cause a magnetic force to be acted all in the same direction, so it will cause the electrons to accumulate at one end of the conductor. So electrons will accumulate at one end and there'll be a lack of electrons at the other end, leading to a negative and positive charge, a plus and a minus. So you've now produced an electromotive force across the conductor. There is an induced EMF in the conductor, and an induced current flows in the conductor if it is part of a complete circuit, and this is what we call the generator effect. Now the change in how many magnetic field lines, the magnetic flux, the conductor cuts through per second determines the force experienced by the conductor, so therefore determines the value of induced EMF in the conductor. So the magnetic flux linkage tells you the number of field lines a conductor cuts, so the change in magnetic flux linkage experienced by the conductor will determine the induced EMF. Now we know that flux linkage is equal to BAN cos theta, so we can link these ideas to form a new equation. Induced EMF is equal to the change in flux linkage divided by time, or delta n phi over delta t. So therefore this shows us that the induced EMF in a conductor is directly proportional to the rate of change in magnetic flux linkage in the conductor. So we know that flux linkage is BAN cos theta, so therefore we can link this in, and we can also move n out of the delta term because the number of turns term isn't really going to change in the generator process. Now this is actually called Faraday's law of induction and determines the magnitude of an induced EMF in a conductor. So we know that flux linkage is directly proportional to time, and we know that the gradient of this line is going to be the induced EMF, and it's common to produce information in examination questions in this format. And we know that induced EMF against time will form the following graph where the area is equal to flux linkage, and once again it's common for examination questions to present information in this format. Now the most common example in the real world of what's going on is a coil of wire rotating in a magnetic field, and we can consider this application in the course and see what's going on. So as the wire rotates, the wire changes its magnetic flux linkage and generates an induced EMF in the wire. Now when the wire is parallel, the induced EMF is the largest, as whilst the magnetic flux linkage is very small, the change in magnetic flux linkage per second is very large. This is because if you can see the values, you can see why. So whilst the values are small, the change is large, and when the wire is perpendicular to the field, the induced EMF is the smallest, as whilst the magnetic flux linkage is very large, the change in magnetic flux linkage per second is very small, as shown with the following terms. Whilst the values are large, the change in values is small. So for a rotating coil, the following graph will be produced. You will get maximum EMF when your flux linkage is a minimum. So here the change in magnetic flux linkage is the largest, so your induced EMF is the largest, and you get a minimum induced EMF here, whilst the values are the biggest, the change in magnetic flux linkage is the smallest, so the induced EMF is the smallest. Now this shows us that the flux linkage and the induced EMF are always 90 degrees out of phase with each other. The flux linkage leads the induced EMF. Now we can link this to the orientation of a coil. The maximum EMF is when the coil is parallel to the magnetic field, as there's the greatest change in magnetic flux linkage. The minimum EMF is when the coil is perpendicular to the magnetic field, as there's the least change in magnetic flux linkage. Now we can also link this into the equation we saw before. So we know E equals N delta phi over delta T, but we know delta phi, the number of flux cut, is equal to flux density times by area, or we can then change area to length times by distance, and distance to velocity times by time. So therefore we can say delta phi equals B LV delta T. Therefore we pop that into the equation, cancel out the time terms in the equation, and therefore get EMF is equal to NBLV. Now this equation is not given to you in your examination book, it's more of a common sense equation, but consider the factors that would affect the rate of change of flux linkage. You've got the amount of flux linkage determined by the flux density, the number of turns of the wire, and the length of the conductor, and the speed at which the field is changing, either the velocity of the conductor or the velocity of the wire. Now remember, in a length of wire or conducting rod, there's only one turn turn, so n can be set to 1. Now this indicates there's a directly proportional link between the speed of the conductor's motion and the induced EMF. Doubling the speed of rotation doubles the maximum EMF, and halving the speed halves the maximum EMF. Now we can further amend this equation to show the direction of the induced EMF in the conductor. Now the induced EMF will always be produced in the opposite direction to the change in flux linkage which causes it. This is Lenz's law. Now this law must be memorized along with Faraday's law of electromagnetic induction. So we know that Lenz's law states that the induced EMF will always be produced in the opposite direction to the change in flux linkage which causes it. If the change in flux linkage is caused by the conductor moving down, the induced EMF is produced upwards in the conductor. This means the following magnetic field is produced in the conductor. So you can see if the motion is going down, the magnetic field is moving upwards. So this means the wire will resist its movement to cause change in flux linkage, as the poles of a conductor and permanent magnet would repel each other. So it leads to an important idea that the production of EMF provides a resistance to its own production. So this naturally limits the largest value of EMF possible in a generator. Now this occurs to prevent the violation of conservation of energy in the universe, as if the EMF was in the same direction to the change which causes it, the following would happen. The production of EMF will cause further attraction between conductor and magnet. This would speed up the conductor and would have the greatest change in magnetic flux linkage and produce a greater EMF. Therefore, this is a positive feedback cycle and would eventually mean infinite EMF is produced and the conductor travels at infinite speed. This will create energy in the universe and is impossible. So Lenz's law has many applications such as back EMF in motors. A motor works as a current passes through a coil. This makes the coil an electromagnet. The electromagnet interacts with the permanent magnet and spins. Now the spinning is occurring as the different sides experience different forces as the current are in opposite directions, but because the motor is also a conductor passing through a magnetic field, as it spins it changes its magnetic flux linkage, so it induces an EMF in the motor. Now Lenz's law states that the EMF is produced in the opposite direction to the rotation of the coil, so we call this idea the back EMF. So the back EMF opposes the current producing the spinning, so reduces the overall spinning. So the back EMF slows the spinning of the motor. So Lenz's law ensures the motors have a top revolution speed. As the faster it spins, the greater the back EMF induced. Now let's consider this with a different example. If we drop a magnet through the air and you drop a magnet through a copper pipe, will the magnets fall at different speeds? Well, yes, they will. The magnet falling through the air will fall quickly. The magnet falling through the conductor will fall slowly, because the magnet that falls through the copper rod takes significantly longer to fall, as when the magnet falls through the copper rod, the effect of the magnet moving through the conductor produces a current in the copper rod conductor. This occurs via Faraday's law. There's a relative motion between the magnetic field and conductor, so the conductor has a change in flux linkage. This induces an EMF and a current. Now as the copper rod is now carrying a current, it also becomes an electromagnet. It produces a magnetic field, but due to Lenz's law, the induced EMF produces in the opposite direction to the change that causes it, so it means the magnetic field is in the opposite direction. So the magnetic field of the electromagnet repulses the magnetic field of the permanent magnet because they're in opposite directions. This opposes the motion, therefore it falls slower. Now the fact that the conductor cutting through the magnetic flux can produce a current is called the generator or electromagnetic induction. So let's now take this to another step. If we drop a magnet through a glass tube, a high resistance iron tube and a low resistance copper tube, which one hits the ground the fastest and the slowest, and why? Well, the magnet falling through the glass tube hits the ground the fastest. The magnet falling through the low resistance copper tube falls the slowest. Why? Well, in the glass tube there's no change in magnetic flux linkage because glass is not a conductor, so there's no repulsive magnetic field. It falls freely. In the low resistance copper tube there's a change in magnetic flux linkage, so there's an electromagnetic induction in the copper. This produces a repulsive magnetic field according to Lenz's law, so the magnet slows down as it falls. Now in the iron tube, whilst there is a resistance there, it'll have the same EMF as the copper does, but because it'll have a smaller current produced because of the high resistance, so the repulsive field produced is smaller, so the magnet will fall faster than the copper because there's less resistance, because there is less actual current produced in the iron. Now, the generator effect can be observed when a coil rotates uniformly in a magnetic field. Now, we know that n phi is equal to BAN cos theta. We can define the angular difference between the conductor and the magnetic field line as phi, as shown on the diagram. So this is then used as to define the angular difference from the center of the conductor. So we know that the angle changes as the coil rotates. So we know n phi is equal to BAN cos theta. So as the coil rotates, phi changes, so the flux linkage varies sinusoidally between plus BAN and minus BAN. This occurs as the direction of the conductor changes in rotation. So as the coil rotates, it is rotating from plus BAN to minus BAN, and we get the following graph. Now we know that's plus BAN, that's minus BAN. Now we can also interestingly remember that the induced EMF is out of phase by the magnetic flux linkage by 90 degrees. This occurs as the change in magnetic flux linkage produces the EMF. So the gradient of the magnetic flux linkage graph is the value of the induced EMF graph. So it shows us one term contains a sine and the other one contains a cosine. So therefore we can link this back in here, because we know the generator effect occurs here when we say n phi equals BAN cos theta. As the coil rotates, theta changes, so how fast theta changes depend on the angular speed omega, where we say theta equals omega t. So we can incorporate this into the equation and say n phi equals BAN cos omega t. Now we can then translate this into the induced EMF equation by saying n phi over t equals EMF. So BAN omega sine omega t. This comes from the product rule of differentiation. When you differentiate cos, because we're dividing by t, we get omega sine omega t. So this shows us that the induced EMF is largest when the conductor is parallel to the magnetic field, because sine 90 sine theta equals 1. So this shows us the maximum induced EMF for a rotating conductor is equal to BAN omega. Now this equation is given to you in your examination book. Now we also note this, that the induced EMF is the largest when the conductor is parallel to the magnetic field. As the conductor moves this alignment, the conductor has the greatest change in magnetic flux linkage per second. Now remember, the induced EMF is caused by the change in the number of field lines being cut, not just the number of field lines being cut. It's the change that you're getting. So when the conductor is parallel, the greatest EMF is produced because you've got the greatest change in magnetic flux linkage. Now when you have the conductor parallel, as shown here, we know that sine 0 equals 0, so sine theta is going to give us a 0 value, so therefore we're going to get 0 for our EMF. So this shows us that when the conductor is perpendicular to the magnetic field, okay, the conductor has the smallest change in flux lines per second, so therefore it is going to give us the smallest value of induced EMF. Remember, the induced EMF is caused by the change in the number of field lines being cut, not the number of lines being cut itself. So when the conductor is perpendicular, you get the smallest EMF induced because you got the smallest change in magnetic flux. So we can link this into that particular idea. So remember, when I look at our graphs, this graph shows us the change in magnetic flux linkage over time for a rotating coil. This now follows the cosine curve, as there's a cos in the equation. So n phi equals BAN cos theta. Now the gradient of the line is the induced EMF of the generator, so therefore we know that this graph shows the change in induced EMF over time for a rotating coil. This follows a sine curve, as there's a sine function in the equation, so it's BAN omega sine omega t. Now this is the trace that will form on an oscilloscope when measuring the induced EMF in a rotating coil, and the oscilloscope trace can then be used to measure the maximum induced EMF, which we will call the peak voltage. Now in theory, the oscilloscope trace can be used to measure the maximum induced EMF in both the positive and the negative, which we call the peak to peak voltage, and if a conductor was placed in a complete circuit, an alternating current will flow in the conductor. Now remember, this trace will form on an oscilloscope which is measuring the induced EMF in a rotating coil, so we'll measure the frequency of an alternating current produced, where the frequency of that current is equal to 1 over the time period. Now the shape of the graph of induced EMF can be altered by changing the speed of rotation or changing the size of magnetic field. Now increasing the speed of rotation would increase the frequency produced, but also increase the maximum induced EMF. Now increasing the flux density would increase the maximum induced EMF, but would have no effect on the frequency. Now remember, when you compare the flux linkage and the induced EMF graphs, you'll know the two values are 90 degrees or pi2 radians out of phase. Now the flux linkage is always ahead of the induced EMF because a change in magnetic flux linkage will produce an induced EMF. Now, the flux linkage curve is a cosine curve and the induced EMF is a sine curve. Now remember, your flux linkage is a maximum at 0, 180, but 0 at 90 and 270, whilst the induced EMF is the opposite. It's a maximum at 90, it's a maximum at 270, and it's a 0 at 0 degrees and 180 degrees. So the instance of being perpendicular, there's no magnetic flux cut, much like at how maximum height an object is stationary, and at the instance of being parallel, the maximum magnetic flux is cut, much like how equilibrium an object is moving the fastest. So let's summarise what we've looked at in today's revision session. The force on a current carrying wire is equal to F equals BIL when the field is perpendicular to current. We know Fleming's left-hand rule, the magnetic flux density, and the definition of the Tesla. We can investigate how the force on a wire varies with flux density, current, and length of wire using a top-band balance. The force on charged particles moving on a magnetic field is F equals BQV when the field is perpendicular to velocity. The direction of force on the positive and negative charged particles, and no circular paths of particles in applications such as cyclotrons. We know that magnetic flux is defined by phi equals BA, where A is normal to A, and flux linkage is N phi, where N is the number of turns cutting the flux, and we link the two by saying N phi equals BAN cos theta. We know the idea of Faraday's law and Lenz's law with some experimental phenomena. We know the magnitude of induced EMF is the rate of change of flux linkage, or N delta phi over delta T, and we know applications such as a straight conduct moving a magnetic field, and that the EMF induced in a coil rotating uniformly in a magnetic field is E equals BAN omega sine omega T. Hope you've enjoyed today's revision lesson on magnetic fields in AQA A-level physics. Thank you very much for listening and have a lovely day.